Why don't we get started? Okay, so today we're going to segue with a set of tools that we're going to need before we do the Poisson distribution, which traffics in events in time. And I promise I will do the derivation of variance for the geometric distribution, but I'll defer that till Thursday. Okay, all right. So why don't we get started? So, who here has learned how to dance? I was young too. Come on. No one, you just sit like there like that and don't enjoy music? No, nothing? Okay, you've learned how to dance. Okay. So when you learn how to dance, what happens? Someone shows you the moves, right? You wiggle like this and you wiggle like that. You put it all together in cadence to the beat of the music, and then you have dance going on. Well, this is what it looks like when a mathematician wiggles like this and wiggles like that. So, anyways, all dancers is wiggle like this and wiggle like that, right? That's just simple. Put the moves together. And so, no, I don't want to do that again. So, how do you approximate a function? You might want to mimic or approximate a function. There's a function f of x. And in order to approximate a function, you need to describe literally how the function wiggles like this and the function wiggles like that. Now, mathematically, when a function wiggles, it changes. And so you have the tools of calculus, specifically the derivative, to tell you how a function wiggles or how it moves and changes. So a polynomial, you remember polynomials, right? Everyone's done polynomials, hopefully. Yes? No? All right, you've done polynomials. So have you ever thought about what a polynomial is? Yeah, I mean, literally the word means many monomials, where a monomial is just a term that involves a square and a constant, some coefficient. But what is a polynomial doing? Have you ever thought about that? Have you ever learned that? Did anyone ever teach you what a polynomial really is doing? What does it mean? No? Okay. Well, it's kind of like dance. It's mathematical dance, and it's teaching you, or showing you rather, how to build up or approximate a function. And just like that dance, you put together wiggle like this and wiggle like that, and you put it all together by summing, and you get some function. And the goal of the polynomial is to approximate some complex function. So if we look at the terms here, right, we have x to the 0 power, and we have x to the k power. Now, when I write it from the small term to the highest order term, right? But you're probably used to seeing it read off. The highest power is on the right, and then the lowest power, x to the 0, is on the left of that sum, right? But it doesn't matter which way you write it, left or right. That's one way of writing it. And each of those monomial terms, x to the 0, x to the 1, x to the 2, has a coefficient. In this case, I call it w, and that coefficient is multiplied by each one of those monomials. Now, of course, you're probably used to seeing something like ax cubed plus bx squared plus cx plus d, and d is multiplied by 1, which is the same as x to the 0 power. You're probably used to seeing the alphabetic characters as your coefficients when you write out a polynomial, but mathematically it's more consistent to use indices, those subscripts w0, w1, w2, because when you have the alphabetic characters, you only have 27 coefficients, whereas if you use a subscript, you can have as many as you need. Okay? So each one of these monomials is a different way of wiggling, moving it, changing. And we'll actually show this in MATLAB. And of course, you can wiggle a little bit, not at all, x to the 0 power, or you can wiggle a lot, x to the k power, where k can be quite big, right? So all the polynomial is really doing is this kind of function dance, if you will. You wiggle like this, wiggle like that, and maybe a little bit of a wiggle that's in between, right? And if you can put them together in the quote unquote right way, right, the correct amount of this and amount of that, you can mimic just about any function out there, okay? So that's really what a polynomial is doing. It's describing the amount of wiggle like this and the amount of wiggle like that for different ways of wiggling. Those are the monomial terms that when you add them, bless you, you get some function shape. You can approximate a function. Now, the nice thing about this polynomial, it's very self-contained. It's kind of neat. You just sum together a bunch of things through some mixture, and you can get just about any function. Well, not any function, but quite a few functions. Okay. Any questions about this? Does that make sense? Okay. So we're going to try this out in MATLAB, but I just want to build a little bit more machinery so that I'm not switching back and forth between MATLAB and the slides. So this is another type of polynomial. Well, do you believe me? Let's see what the ingredients are. We have a set of monomials. So here we have x to the 0 power is 1, x to the 1 power, x to the 2 power, x to the 3 power, and so forth. Okay, well, this is absolutely a polynomial, but we have some peculiar weights for this particular polynomial, right? These weights involve some constant, and it involves the derivative of a function, and that derivative of a function is evaluated at the 0 point at origin. So yes, you could consider some coefficient w times x squared, but it's just a really peculiar type of coefficient. Now this coefficient just happens to involve a derivative. So what does that mean? That means if you want to describe a particular function as a polynomial, this sum of monomials, a little bit of this, a little bit of that, then you can do that as long as you have the defined derivative of that particular function. Does that make sense? Any questions? So this particular polynomial has a special name. It's the Maclaurin series. And the Maclaurin series is nothing more than a polynomial with these peculiar coefficients created by this Maclaurin person, right? Now, Maclaurin series is a special case of a so-called Taylor series. A Maclaurin series is a Taylor series about origin. Taylor series is shifted to an arbitrary place on the number line, okay? All right, so we have this other polynomial, our Maclaurin series, and it's just like any other polynomial, except there's a particular recipe about how you pose these coefficients, W0, W1, W2, and so forth. Okay, so let's write that polynomial, this Maclaurin series, a little bit more compactly to reveal what these coefficients are. So we have a sum for I goes from 0 to n, and then we'll notice here x, our monomial, has an exponent which is the same as this index of the summation. So we're going to have a term x to the 0, which is 1, plus another term x to the 1, x squared, x cubed, x to the 4th, and so forth. So this other stuff, that is our coefficient w. You could just imagine all of this is some w, and that w has an index, w sub I, so w0, w1, w2, and so forth. And w takes on a value of the product of two things. One is 1 over I factorial, right, which is a number, it's a constant, right? If I is 0, I factorial is 1, so that's 1 over 1. If I is 2, I factorial is 2, so that's 1 over 2. So that's nothing more than a constant. And then this other part is the ith derivative of a function evaluated at 0. You take a function, you take its ith derivative. So if it's the 0th term, the ith derivative, the 0th derivative is nothing more than the function. The first derivative, you take the first derivative. Second derivative, you take the derivative twice. Third derivative, you take the derivative 3 times. And when you get that derivative, you then plug in 0 evaluate that derivative at 0, and that's another constant. So you multiply those two constants together, and that's your W for this Maclaurin polynomial. Okay? Now, it kind of almost makes sense. If you want to approximate how a particular function wiggles, wiggle like this, wiggle like that, you need to know how that function changes. And one way to describe how a function changes is by its derivative. Now, the higher the order of the derivative, meaning like second derivative, third derivative, fourth derivative, the more intense that wiggling is. And what it says is that essentially for each monomial, right, x to some power, you're going to use an increasingly larger or intense coefficient to add more of that intense wiggle. Okay? All right. Any questions about this? Does that make sense? Yeah? Okay. So what we're going to do in MATLAB is I'm going to show you what the polynomial is doing, right? And we'll actually bring in terms of the polynomial and actually see plots of that. And then we're going to develop the approximation of the Maclaurin polynomial, and we're going to use that to approximate the function sine x. Okay? All right. Any questions about this? Make sense? All right. So let's do that. Let me pop out of here. And let's go into MATLAB. Okay, so let me create a new script, and I'm going to call that test polynomial. So let me save that. Test polynomial. Okay, I don't have my other glasses, so let me take these off. All right, so test polynomial. So we're going to start out with values of x. So I'm going to say x goes from minus 100, minus 100, increase by 1/100th up to positive 100, right? So I'm just going to have a bunch of values here, 10,000 values of x in regular increments along the real number line. So now I'm going to have some weights. Let's have weight W0 is equal to 1. Weight W1 is equal to 1. Weight W2 is equal to 1. And let's have W3 is equal to 1. So those are our coefficients for the monomial terms, the 0th term, first, second, third, and so forth. So now we're going to say x, let's call that x naught terms, is equal to power x raised to the 0 power, right? So I'm going to raise all my x values to the 0 power. That's going to be the 0th monomial. And then likewise, I'm going to do the same thing with the first power, power x raised to the first power, and then x squared, so that's raised to the second power, power x 3, I'm sorry, x2. And then likewise, I'm going to do x 3 power x3. And let's, for good measure, let's go up to the 4th monomial, x4 power x, all my x values, raise it to the 4th power. Okay, so I'm going to use a coefficient W4 equals 1. Okay, so now let's take a look at the wiggle, so to speak, or the rate of change of each one of these different monomials. So let's say my f of x is equal to W0 times x0, right? So that's that first term of the monomial, and I'm going to plot x and f of x, x versus f of x. Display done, and I like to do a display done just so I can have a breakpoint at the end before the function exits. Okay, any questions about this? So it's just a basic polynomial. Each of the weights is equal to 1. So let's try out that first term, W0 times x to the 0 power. So I do that display, and I get a constant. You'll see on this chart here, right? That's a constant line going from left to right, and it passes through the y-axis at 1, right? And 0 is all the way down here at the bottom of my display, right? So it's a constant. That does not wiggle very much, right? So you could call that a 0th order wiggle. It doesn't wiggle at all. Okay, so now let's see what happens. Quit the debugger. If instead of W0 X0, I say W1 X1, right? Now W1 X1, all right, that's just W1 times X. X is to the first power, so it's just W1X. So let's see what that gives us. So I plot that, and we see a 45-degree slanted line going from minus 100, minus 100. It passes through the origin, 0, 0, at the center here, and then it goes up to the right, right? So that's another way of wiggling. It's a constant increase, right? That's a way of wiggling. It's not very interesting, but it wiggles more than X naught, W naught, right? Because that's just straight across. It doesn't go up and down at all. Okay, so now let's take a look at what happens if I use the third or the second order monomial. I'll say W2 times X2. And remember X2, it was the second power, right? So that's squaring. It's going to give me a parabola. So I run this, and you'll see, there's my parabola. I start up high, and I come down, and I turn the corner at origin, and I come back up again. That's another way of wiggling, right? This one changes even more than the straight line x1, w1, right? That changed, and then x naught, w naught, that didn't change at all. So as you can see, as you increase the order of the monomial, if you increase the power on that monomial, it wiggles even more and more and more. So let's see how that plays out with the third order and the fourth order. So let's say W3 times X3, right? That's going to give me a spline curve, right? So it's going to be even more wiggly than a parabola. Yes, it is more wiggly than the parabola. It changes more often, and it changes more dramatically. All right, so let's try W4 X4, right? That's a fourth order spline. So let's save that and run it, and let's see how it wiggles. Okay, wow, that changes even more dramatically. It's not a parabola. The parabola didn't curve as dramatically. You see this drops very, very quickly, and then it goes into a flat bowl shape, and then it increases very rapidly, right? And so as you increase the order, and you'll notice here, this is, if you look at where it intersects origin, it's 10 times 10 to the 7 power, right? So that's a pretty dramatic drop in just going from minus 100 to minus 20. It drops from 10 times 10 to the 7 power all the way down to 0 in a short space, right? So that is a really dramatic change. So we have this idea that each one of the monomials of different order is a function that wiggles not at all to a little bit to more dramatic to even more dramatic, and it gets increasingly wiggly as you increase the order, the power on the monomial term. Okay, any questions about this? Does that make sense? Okay, so now this idea of combining them allows you to now use a little bit of this, a little bit of that, and you can use that to try to approximate the shape of some arbitrary function. So let's look at combining some of these monomials. Okay, so we have our x naught, w naught, right? That was a straight line. And then we have our x1. So let's add those two terms together. So w naught times x naught plus, let's add w1 times x1. So what that does, it takes that constant, which has the effect of raising or lowering something up or down, and it adds it, in this case, to that constant slope 45-degree line. So the result of this is going to raise up a constant slope 45-degree line. So let's try that out. So right now, the coefficients are both 1, so it's going to be equal parts of both types of wiggles, the nothing wiggle and the constant increase wiggle. All right, so let's try that out and see what happens. So if I do this, now we notice here that we have our 45-degree lines. That's not too easy to see. And it's just a little bit, if you notice right there in the corner, in the lower left-hand corner, it's not at negative 100, negative 100. It's just a little bit more positive than negative 100. Let's change the coefficient on the constant to see what happens. What if we change W0 to 100, right? So now it's going to say, I want 100 parts constant wiggle and add that to 1 part um, slope wiggle, right? That first order wiggle. So I'm adding the two things together, that constant, which is no wiggle, and that constant slope, which is a very slow wiggle. So let's try that. So you notice here now, I took my 45-degree line and I raised it up a constant, and that constant was 100. And you notice here, this 45-degree line, it pierces the vertical axis, the y-axis, at 0, at minus 100 comma 0, right? It's no longer minus 100 comma minus 100. You notice that? So I've combined the two ways of wiggling or changing, and now I have a different function, okay? All right. So we can see this a little bit more dramatically if we take our constant, and let me change that coefficient back to 1, and let's combine the parabolic function, right, that parabolic wiggle, with that no wiggle, right? And let's see what we have. So remember, the parabola, it went through origin and scooped back up. So let's save that and let's run it and see what happens when we add our W naught X naught, or x to the 0 power, to the W2 times x squared. So we do that. Well, it's kind of hard to see because it's only raising it up 1, but let's now increase our coefficient to say 50 on the W naught term. Let's save that and let's rerun it. And you'll notice here, right, our parabola, it kind of should be raised up. Let me see, W2, X2. That's a lot harder to see. Let me make that 100. Let me do it that way. Save, run. Okay, so you'll notice here, it's kind of hard to see. I should change the scale. That this parabola, it doesn't touch the x-axis. It's above the x-axis. And it's above the x-axis, you'll notice here, right around, well, just at 100. So if I go here right at origin, it doesn't actually touch. It's at 0 comma 100, right? And so that x naught w naught took that parabola and picked it up in the y direction. Okay, all right. Likewise, and this is the last one I'll do for the basic polynomial. Let me take the w1 x1, and we'll take the polynomial. First, I'll turn off the 0 term by making w naught 0. And if w naught is 0, that means that w naught x naught doesn't matter. So here we just have w2 x2, which is just our plain vanilla parabola. And you'll notice there's my parabola. And just to show you that it touches 0. So here, when the x-axis is 0, its y value is 0, right? So it passes through the origin at 0, 0, right? Okay. Any questions about this? No, make sense? So now let me take this parabola, and you notice the shape. It's symmetric, right? It scoops at the same rate. It increases. And if you were to draw a vertical line that passes through x equals 0, it would be a mirror image on both sides of that vertical line. It's symmetric about the y-axis. Now, when I take this parabola, this w2 x2, let me add to it w naught, but I'm going to add 5 parts of, nope, let me see, that one. I'm going to add 5 parts of w1 x1, right? And I'm going to add that to the parabola. And remember that w1 x1, it was that line slanting at 45 degrees. So I'm going to disturb my parabola, and I'm going to add when x is small, I'm going to add small amounts. When x is large, I'm going to add larger amounts. So essentially what that's going to do, it's going to tip the parabola, and it's no longer going to be symmetric, okay? So let's take a look at what the result of that is. So it's 5 parts W1 x to the 1 and 1 part W2 times x squared. So let's save that and let's run it. And you'll notice here that the right-hand side is higher than the left-hand side. It's no longer symmetric. We can make this a lot more dramatic if we increase the coefficient to, say, 100 for the x1 W1 term. So let's save that and let's rerun it. And you'll notice it's even more dramatic. If you look at the parabola, you notice the left-hand side of the parabola, well, it's really, really low. It doesn't scoop quite as much or as high as the right-hand side of the parabola. And so you can imagine two shapes at play. You have one function. Let me do it this way. You have one function, which is the parabola, and then you have another function like that. So if you're adding, right, this negative tends to want to pull the parabola down, and the positive wants to push the parabola up higher, right? And so you get that parabola kind of tipped up like that, kind of skewed. Okay? Any questions about this? So what this polynomial is doing, it allows you to mix together different ways of changing or wiggling in order to construct an arbitrary function. Okay? All right. Any questions? Make sense? So our whole purpose was to talk about this Maclaurin polynomial, but you have to first talk about polynomials before you can talk about the Maclaurin series. And the point of a Maclaurin series is to now use these peculiar coefficients in a polynomial. And these peculiar coefficients involve the derivative of a function. So let's take a look at that. So the function that we're going to approximate is the sine function. So let me create a new script. And we'll just call it test Maclaurin. I think it's sine. Okay, save. So let's first look at the sine function, ground truth, and start from there. So we're going to say our theta, or x, is equal to, and we're going to go minus pi, increasing by 0.01 radians up to positive pi. I think that's how you say pi. Let me make sure. Help pi. Yep, that is pi. Okay, easy as pi. All right. So now we're going to create do a plot. X equals sine x equals sine of our x variable, right? So then we're going to plot all of this. So we're going to say plot x versus sine x, right? And we're going to plot it from negative pi, which is 180 degrees, to positive pi, which is positive 180 degrees. So that gives us a whole 2 pi radians for one cycle of the sine function. Okay, so I'm going to set the axes. I can't remember how to do that. Help axis. And you give it the x and the y range. And we're going to set the axes so that this thing stays the same size, same scale. X min, X max, Y min, Y max. So we're going to say axis, and the X min is going to be minus pi. The X max is going to be positive pi. The Y min sign varies between plus and minus 1. So we're going to say negative 1, and we're going to say positive 1. Okay, so do that. And let's save that and see what we get. All right, display, done. Okay, save. And let me set my breakpoint, and let's try this out. So there's our sine wave. Okay, it's not too interesting. Maybe I should do it a little bit more than one, just so you can see the top of it and see it turn instead of being clipped at the top of the screen. So the 1.4 1.4. We'll do it that way. Save, run. All right, so there we go. So there's a single cycle from minus pi to positive pi. Oh, what did I do? Yeah, that's right. Of sine x. Okay. 2 pi radius, 2 pi. Yeah, that's fine. Okay. All right. Any questions about that? That's our ground truth sinusoid. So now what I'll do is uh, create the Maclaurin series and approximate this sine wave, that's the actual sine wave, with our Maclaurin series, and show you that as I include terms in this polynomial that are more and more wiggly, right, the higher order terms, the higher order monomials, that it'll get closer and closer and closer to approximating the sine wave. But I'm going to set the coefficients differently using the Maclaurin series. Okay? All right. So let me bring this up so I can remind myself what the Maclaurin series is. And so the first thing I'm going to need, if I want to approximate a sine function, I'm going to need the derivatives of the sine function, right? So we'll go back to calculus, and I'm going to create a new function, and this new function will compute the kth derivative of the sine function. And we're going to make some observations when we do this. Okay, so I'm going to save it, and it's going to be a function, and it'll be kth derivative of sine x. All right, and so it's going to be a function. So result function result equals kth derivative of sine x. And so what I'm going to do is I'm going to give it k, so I know which derivative it is, the zeroth derivative, the first derivative, etc. And I'm going to give it x, the value that it's going to use for the derivative. Okay, so now I'm going to say result equals 0 in the beginning, and then we'll fill in a couple things. So the first thing I want to do, and I'll ask you, let's take a look at the sine function. We need to compute the kth derivative, and we want to do it in a function. So let's first work through a few iterations of the derivative of the sine function and see if we can recognize a pattern. So this is the order, right? This is I, right? Order I, right? And this is I dx of sine of x. Okay, so if our order is 0, we're not doing any derivative, and that's just what? Sine x. Okay. Now, what is the first derivative of sine x? Cosine. Cosine x. Okay. So how do you do the second derivative of sine x? It's negative sine x. Okay. So it's just ddx of whatever the first derivative was. So it's minus sine x. Okay. What is the third derivative? It's negative cosine. Okay, so it's just minus it's ddx of this, so it's minus ddx of sine x minus cosine x. Okay, what is the fourth derivative? Is sine x. Okay, so fourth derivative, sine x. Oh, wait a minute. It cycles. It goes back here. So every fourth order, every modulo 4 for the ith derivative, we're just going to select either the 0th, first, second, or third derivative. Does that make sense? Okay, so we can absolutely program this. What we do is we say, okay, we take I, or in this case for the function k, because it's the kth derivative, and we select order is equal to, in that case, if it's that function, k modulo 4, where 4 is the number of times we apply the derivative before we cycle back, right? So we apply the 0th time, first, second, third. If we apply it again for the fourth derivative, the value goes back here, right? So that means modulo 4. Does that make sense? So every 4 our derivative is going to go back to the same as the 0th order. Okay, so we're going to start out and we're going to say order equals k mod, well, let's like have a variable. So cycle of sine x is equal to 4, right? So we take k and we do modulo. Let me make sure I remember how to do that. Clear, CLC, help, mod. Okay, so it's mod of k with the cycle of sine x, right? So that's the same mathematically, I'll put it in a comment, of saying k mod cycle sine x, which is the same as k mod 4, right? So if you had a different function and the cycle was more than 4, you would do the same thing, right? So now what we're going to do is we're going to use a switch statement now to execute whatever that, to implement whatever that kth derivative is, and we're going to evaluate that it at that x value. Okay, so let's go look at what the switch statement is. Help switch in MATLAB. So we have switch the value and then a bunch of cases. Okay, all right. So let's write switch order, right? Case 0, case 1, case 2, and case 3. Okay. So for and the default, well, we're not going to have a default because it doesn't it's definitely one of these. End. So we end the switch, and then for each case, I'm going to say result equals sine of x. So we execute sine if it's 0th order. Result equals, that was cosine x if it's first order. If it's second order, that was what? Minus sine equals minus sine x. And then result, what did it do? In case something else happening. And then the third one, result equals minus cosine x. Oh, something's happening. All right, so let me save. Oh, yeah, right. Okay, forgot about that. Okay, so we do that, and this is our kth derivative of sine x, right? So if we said sine, the 0th derivative, that's sine. If we said the third derivative, that's minus cosine. If we said the fourth derivative, mod would return back 0 because 4 mod 4 is 0, and then we'd do the sine x. So that looks like it'll work. Okay. Any questions about it? Any questions? Make sense? Okay, so that's our implementation of the kth derivative of sine x evaluated at some value x. Okay, so now we want to actually run the Maclaurin series for this. And the Maclaurin series, so let me see. Let me create a new function and let me save. And that's going to be Maclaurin of sine x. And that's going to be a function. So I'm going to say function result equals Maclaurin of sine x. And that's going to take a couple things. It's going to take n, the number of terms in the Maclaurin series, And so if I have a polynomial, remember that that polynomial, Maclaurin series, is nothing more than a polynomial. And I need to know what's the highest order of that polynomial, right? The highest order, let me call it D instead of N, just to make it a little different. So it's going to be a dth order polynomial. So D is going to be 0, 1, 2, 3, 4, 5, 6, 7, up to and including D. And that D is going to tell me how many terms I have in the Maclaurin series, which is the same as saying what is the highest power in my polynomial, right? Because as your monomial gets higher and higher in its exponent, it's going to be more and more wiggly, okay? So that Maclaurin of sine x is going to be an approximation, and I'm going to evaluate it at that point x. It's an approximation for sine x. Okay, does that make sense? Any questions? All right, so let me save that. So now I'm going to loop, and in that loop, I'm going to compute a partial sum. So partial sum started out as 0, and then I'm going to loop for I goes from 0, increment by 1, up to D, because that's the order of the polynomial, and I'm going to end that for loop. Okay, so what am I going to do in each iteration of this for loop? Each iteration of this for loop corresponds to one term. Now remember, I had that peculiar weight, and then I had this polynomial term. Now this polynomial term, I'm just going to write out polynomial term, started out as 0, and I'm going to note the two other terms here. So that weight, or each term in my Maclaurin polynomial, is going to have a polynomial term, which is x to some power. It's going to have a factorial term, which is 1 over I factorial. And it's going to have that derivative term, which is the kth derivative, evaluated at 0. Well, I just did the kth derivative of sine x, so that will take care of my derivative term. So I have something called a polynomial term. I have a factorial term, and I have a derivative term, right? So on each term in my Maclaurin polynomial is going to be the product of those three things. It's going to be the polynomial term, x to the I power, the derivative term, the ith derivative of my function sine x evaluated at 0, and the factorial term. Okay, so my polynomial term, polynomial term, is just going to be power. I'm going to raise x to that power I, x to the ith power. Okay, there's my polynomial term. So now my factorial term is going to be 1 over the factorial of that particular index. So factorial of I, right? So if we look back at the Maclaurin polynomial, it's 1 over I factorial. So here I take for my factorial term 1 over factorial of I, where I is that index for the summation. Okay. Did I spell something wrong? Polynomial term, factorial term, partial sum. Okay. So now I'm going to use do my derivative term. Derivative term is equal to kth derivative of sine x, right? The ith derivative, and I'm going to evaluate that at 0, right? And that's exactly what my derivative term is. It's di dx, the ith derivative with respect to x of that function, and you evaluate it at x equals 0. Okay. Any questions about this? Make sense? Okay. So let me save this, and then I'm going to multiply these together. So I'm going to say um, monomial, see the monomial, 0. So I'm going to say the monomial is equal to polynomial, derivative term to make it match the other one. So it's derivative term times factorial term times polynomial term. So derivative term times factorial term times polynomial term. Okay, There we go. So now I say partial sum is equal to partial sum plus the monomial, right? So now I'm adding that term. Okay, so let me save this. And I don't know why it's the value assigned might be unused. Tails. Okay, I don't want them to be local. Oh, come on, shouldn't matter. All right, I'll just ignore that. So result. Okay, yep, sorry, I forgot that. All right, so now result equals partial sum. There we go. Forgot the return. Okay. It doesn't like me doing these. All right, fine. Just get rid of the warning. If you reuse variables on multiple iterations of the loop, it's actually more efficient to allocate them before and not have to reallocate them and delete them each time. But I'll just satisfy the warning here and do that. So this is my Maclaurin series for sine of x. Okay. So now let's look at where was it? Maclaurin sine, test sine. Okay, so here we have sine x, right? This is our original sine x, and we're going to compare this to the version of sine x approximated by summing together wiggliness of various sorts as prescribed by Maclaurin. Okay, so this is our original sine x, right? So it displays our sine x, and there it is in figure 1. Okay, so let's now um, call sine x m, the Maclaurin version of sine x, and we will say Maclaurin sine x, and we have to give it an order of the polynomial or degree. So degree is equal to, let's say we wanted a degree 2 polynomial, which isn't very interesting. So we're going to say the degree of the polynomial, degree, and we're going to say give it the x array, and it'll apply that to each element of the x array. So now we're going to plot sine x and then hold on, keep the graph, don't wipe it away and plot anew. Plot x against sine xm, which is the Maclaurin version of our sine wave. Okay, so if I don't have any bugs, we'll see. Then what you'll see in one color is the original sine in blue because it's plotted first, and then the second one should be the approximation in red. So if we see this, well, it's a second order approximation, the Maclaurin, and you'll notice it does a pretty lousy job. It gets some of the sine wave wiggliness, the sine wave in blue, but the red, it gets that part here in the middle, but it does a lousy job of kind of turning the corner here for that bowl here and that the convex and the concave portion of the sine wave, right? So it does a horrible job for second order. Well, let's see what a first order looks like. That shouldn't be at all very interesting because it's just a constant line informed by the slope of the sine wave. Well, it doesn't do very well. Okay, so let's now make it a degree 3 Maclaurin, right? So let's save that and run it. And we see here, oh, wait a minute. The blue is the original sine wave. The red is the approximation from Maclaurin. So now we're bringing in that third order wiggliness, right, with coefficients informed by the third derivative of the sine wave. So you notice here the red, it turns, but it doesn't quite, turn the same way. It lines up precisely in the middle here. The red's right on top of the blue, but then the blue doesn't turn as dramatically. The red kind of scoops down really quickly. So it's trying to approximate. Let's bring in a little bit more wiggliness, degree 4 wiggliness, and see how that Maclaurin approximation does. So when we run that, we see, all right, it's getting closer. It's closing the gap in places where it didn't track with it before. So that's degree 4. Let's try degree 5 and see what happens, right? So we'll run that, save, and we run it at degree 5. Well, wait a minute. It's kind of getting even closer. It kind of overshoots it a little bit, right? It thinks it's trying to turn when the sine wave is going straight, the blue, right? But it's getting closer. That gap between the approximation in red and the actual sine wave in blue, they're getting much, much closer. Okay, that's good news. So let's say degree 6 wiggliness. So that means a polynomial with x to the 0 power up through and including x to the 6 power, right? So let's save that and let's run it and see what happens. All right, it's kind of trying to. All right, so let's see if we can get degree let's try degree 8 instead of just going by ones in the interest of time. So let's save that and let's try it and run it, see what happens. Oh, wait a minute. It's almost spot on. There's a little bit of a gap on the first pi over 2, right? So you'll see here the blue and the red are separated a little bit here, but it, for the most part, coincides almost everywhere else. And you see the first pi over 2 and the last pi over 2, it kind of separates a little bit, right? Okay, so let's try degree 9. Give it just a touch more wiggliness, right? Order 9, and let's see what happens. So let's run this. And wait a minute, can't tell the two apart. You can't at all. They're perfectly coincident with one another. So let's try, see what happens instead of pi if we went minus 2 pi through plus 2 pi. See if we can do 2 cycles and see what happens. If we can preserve through, yep, ninth order does it. So here we can do 1 pi, we can do 2 pi, and guess what? Ninth order Maclaurin approximates it perfectly. Okay? All right. Any questions about this? Bless you. Any questions about this? Does that make sense? Okay. And so we started out with what a polynomial means, and we took that and plotted out different order polynomials, wiggliness, if you will, speaking more casually. And then we have this special polynomial whose peculiar weights involve the derivative and a factorial. And we constructed the Maclaurin series by taking the function we want to approximate. We computed the kth order derivative by starting with the 0th derivative, the first, the second, third, fourth, and so forth. And we recognized the fact that there's a cycle here. And of course, you need to have a cycling because if you want to implement it, you need to have a value for arbitrary inputs of k for the kth order derivative. And we took that and we created our Maclaurin series for sine x. So we computed the polynomial term, the factorial term, the derivative term. We multiplied the three together to get each term in the Maclaurin polynomial. And then we added them together to get the approximation where you're just summing together literally different little bit of this, little bit of that on the wiggliness in order to approximate a function. So then we call that in our test and we can see we need a degree 9 Maclaurin polynomial in order to approximate the sine function. Okay. Any questions about this? Does that make sense? Okay, so when we talk about the Poisson distribution, you will see the Maclaurin series, but I wanted to take this opportunity to try to re-explain, hopefully, in a way that is more accessible, what a polynomial is, and more importantly, what the Maclaurin series is. Now, certainly in probability and statistics, you make use of Taylor and Maclaurin series for derivations, and these approximations are really important in computer science in general, because you'll notice here I needed 9 terms to approximate the sine wave. Now, suppose if you were on a watch platform and you wanted to generate a function or evaluate a function, and your platform didn't have a lot of computation power, then what you could do is you could say, okay, well, I'm willing to trade off accuracy against computation. So if I want to compute something that looks like a very weak sine wave, right? I don't need to have it completely accurate because I don't have the amount of MIPS that I need or compute power in order to compute it precisely. Then I might say, okay, I'm willing to say degree 4 and just deal with the fact that it's not 100% accurate. That's a little bit different, as you can see here with the degree 4. It gets it, where pi is, pi in the middle, right? The middle pi radians worth of sine output. But for the first pi over 2 and the last pi over 2, it's off. And so what these Maclaurin and Taylor series allow you to do is to trade off accuracy against compute power, because the more orders the degree has, the more compute power you need. But certainly, we only needed 9 in order to be spot on with this approximation of sine x. Okay? All right. Let me just rerun that and leave it there. Save. Degree is 9. There we go. Back to where we were. Okay. Any questions about this? Does that make sense? So here we are. We have the red perfectly superimposed with the blue, at least by my eyeballs. All right. So there's our approximation, and the Maclaurin series is a way of approximating an arbitrary function, only you're taking your regular polynomial and you're replacing the coefficients with these peculiar coefficients prescribed by Maclaurin. And we can compute that for any function, and we can mechanize that computation by looking at the cycle time for the kth derivative of our function. So that's the end, and there's a URL there for Khan Academy. They do a fantastic job in talking about the Maclaurin series and the Taylor series. So please make sure you go through that and don't just go through it passively. Actually get a pencil and paper and actually kind of sketch it yourself and convince yourself that it works. And so we will pick up on Thursday with the Poisson distribution, and we will make use of Maclaurin series for the Poisson. You need that to show total probability and mean. Okay? All right. Any questions about this? Is this helpful? Okay. So I will see you all on Thursday. I'll end there. And I think we're ending a little bit early. Yes, we are. Okay, so I'll see you all on Thursday.